let yourself settle into a comfortable position, somewhere your body can truly relax. Feel the weight of the day beginning to lift from your shoulders like morning mist evaporating in gentle sunlight. Take a slow, deep breath, feeling the air move through you, and as you exhale, release any lingering tension. Tonight, we're going on a journey to the very edge of existence itself, to a time when the universe was so young that what we're about to explore simply shouldn't have been possible. We're going to discover something remarkable together, something that has astronomers questioning everything they thought they understood about how the cosmos came to be. But there's no need to grasp every detail or memorize every fact. Just let the story wash over you like waves on a distant shore, painting pictures in your mind of a universe stranger and more wonderful than anyone imagined. So close your eyes if you'd like, or let them rest on a distant point, and drift with me into the cosmic dawn. Before we begin our journey into the impossible, if you're enjoying these explorations of the universe's mysteries, please take a moment to like this video and subscribe to the Science Pillow. Your support helps us continue bringing you these calming journeys through science and space. And now, let's discover what James Webb found that shouldn't exist. The James Webb Space Telescope, humanity's new eye. On Christmas morning in the year 2021, something extraordinary happened. From the European Space Agency's launch site in French Guiana, a rocket lifted off carrying the most ambitious scientific instrument humanity had ever built. The James Webb Space Telescope, folded up like an intricate piece of cosmic origami, began its million-mile journey to a point in space where the gravity of Earth and Sun balance in perfect harmony. For more than 2 decades, thousands of engineers, scientists, and technicians from 14 countries had poured their expertise into this marvel of technology. They'd created a telescope so sensitive that it could detect the heat signature of a bumblebee at the distance of the moon. They'd built mirrors coated in gold so thin that if you gathered all the gold from the entire telescope, it would barely form a sphere the size of a large marble. They'd designed a sun shield the size of a tennis court, made of material thinner than human hair, capable of blocking enough heat to protect ice cream sitting on the sunny side while the shadowed side dropped to temperatures colder than the darkest regions of outer space. But why? Why did humanity invest $10 billion and 25 years into this single instrument? The answer lies in a fundamental limitation of all the telescopes that came before it. The Hubble Space Telescope, Webb's predecessor, had revolutionized our understanding of the universe for 3 decades, revealing breathtaking images of distant galaxies and nebulae. But Hubble sees primarily in visible light, the same light our eyes detect. And visible light, it turns out, can only show us so much of the universe's story. When we look out into space, we're also looking back in time. Light travels at about 186,000 miles per second, the fastest speed possible in our universe. That sounds incredibly fast, and it is, but the universe is so vast that light from distant objects takes millions or billions of years to reach us. When we observe a galaxy 1 billion light-years away, we're seeing it as it existed 1 billion years ago, when the light we're now detecting first began its journey across space. The most distant galaxies, the ones that formed in the universe's youth, lie so far away that their light has been traveling toward us for more than 13 billion years, nearly as long as the universe has existed. But there's a catch. As the universe expands, it stretches space itself, and this stretching affects light traveling through space. The wavelengths of light get stretched along with space, shifting toward the red end of the electromagnetic spectrum in a phenomenon called redshift. For the most ancient and distant galaxies, this redshift pushes their light beyond the visible range entirely, into the infrared part of the spectrum that our eyes can't see. This is where James Webb transforms our cosmic vision. While Hubble struggles to see much beyond about 12 billion years into the past, Webb was specifically designed to operate in the infrared. Its instruments can detect wavelengths of light up to 28.5 micrometers, which allows it to observe galaxies with redshifts greater than 9, peering back to when the universe was less than 500 million years old. This capability means Webb can witness something Hubble never could: the cosmic dawn, the epoch when the very first stars ignited and the first galaxies assembled from the primordial hydrogen and helium that filled the infant universe. The telescope's mirror exemplifies its extraordinary engineering. Instead of a single solid piece of glass like most telescopes, Webb's primary mirror consists of 18 hexagonal segments, each made of beryllium and coated with a microscopically thin layer of gold. These segments work together as a single mirror 6.5 meters across, over 2.5 times larger than Hubble's mirror. But they had to be folded up to fit inside the rocket that launched them. After Webb reached its destination, a complex ballet of machinery unfolded these segments and aligned them with such precision that the entire surface is smooth, to within 1/10,000th the width of a human hair. The sun shield presents its own engineering miracle. This 5-layer barrier, each layer separated by a vacuum gap, protects the telescope's instruments from the sun's heat. The side facing the sun reaches temperatures of about 85 degrees Celsius, hot enough to boil water, while the shaded side plummets to minus 233 degrees Celsius, colder than liquid nitrogen. This temperature control is crucial because infrared observations require incredibly cold instruments. Any heat would create interference, like trying to observe faint stars through the glare of streetlights. Operating from its position at Lagrange Point 2, roughly 1 million miles from Earth, Webb orbits the Sun in synchrony with our planet, always keeping the Earth, Sun, and Moon behind its sunshield. From this vantage point, free from Earth's atmosphere and thermal radiation, Webb can observe the universe with unprecedented clarity and sensitivity. When the first test images arrived in July 2022, the world held its breath. The first deep-field image, showing a tiny patch of sky packed with thousands of galaxies, some of them more than 13 billion light-years distant, exceeded even the most optimistic expectations. The detail, the clarity, the sheer wealth of cosmic structures visible in that single image told astronomers they were about to witness revolution in their field. But nobody was prepared for just how revolutionary these discoveries would be. Within months of beginning its science observations, Webb started sending back data that fundamentally challenged our understanding of how galaxies form and evolve. The telescope had been designed to answer questions about the early universe. But instead, it began by questioning the answers we thought we already had, the discovery that changed everything. In the Netherlands, a graduate student named Martijn Oe was analyzing data from another telescope entirely when he discovered what would become the largest known structure created by a single galaxy. His serendipitous finding reminded astronomers that the universe constantly surprises us when we look with fresh eyes. But thousands of miles away, another team was about to receive an even bigger surprise from the James Webb Space Telescope's unprecedented observations of the cosmic dawn. The team, led by Ivo Labbé from Swinburne University of Technology in Australia, had submitted a proposal to observe a particular patch of sky near the Big Dipper constellation using Webb's near-infrared camera. This region had been previously imaged by Hubble as part of routine surveys, and it appeared relatively unremarkable. Just another field of faint, distant galaxies among the countless millions scattered across the heavens. The team wanted to use Webb's infrared vision to identify galaxy candidates from the first billion years after the Big Bang, expecting to perhaps confirm a handful of extremely distant but small and faint proto-galaxies. What they found instead left them stunned. Erica Nelson, an assistant professor of astrophysics at the University of Colorado Boulder and a co-author on the study, expressed the team's reaction with characteristic scientific understatement that barely concealed their amazement. "It's bananas." This simple phrase, appearing in the university's press release, would capture headlines around the world because it conveyed something that technical jargon never could: that serious astronomers, people who spend their careers studying the universe's most extreme phenomena, had encountered something so unexpected that it defied their professional composure. In Webb's images, 6 fuzzy red dots stood out against the cosmic background. At first glance, they didn't look particularly special, just small, reddish blobs among thousands of other objects in the frame. But when the team analyzed the light from these objects, measuring their redshifts to determine their distances and their brightness to estimate their masses, the numbers didn't make sense. These weren't the faint smudges of newly forming galaxies that theory predicted should exist 500 to 700 million years after the Big Bang. Instead, they appeared to be mature, massive galaxies, each containing almost as many stars as our present-day Milky Way galaxy. To appreciate how shocking this discovery was, we need to understand what astronomers had expected to find. According to the standard model of galaxy formation, the early universe should have been populated by small blue galaxies undergoing their first bursts of star formation. These infant galaxies might contain a few million to perhaps a billion stars at most. Tiny compared to modern galaxies like the Milky Way, which hosts somewhere between 200 billion and 400 billion stars. Moreover, these early galaxies should be blue, the color of young, hot stars, not red, which indicates older, cooler stars that have been burning for hundreds of millions or even billions of years. But Labbé's team was looking at galaxies that appeared to have tens or even hundreds of billions of stars, existing at a time when the universe itself was only 500 to 700 million years old. Even more puzzling, these galaxies glowed red, suggesting they contained populations of older stars. It was like opening an album expecting to see baby pictures and instead finding photographs of full-grown adults. The timeline simply didn't work. Joel Leja, an assistant professor of astronomy and astrophysics at Penn State and one of the study's authors, laid out the problem clearly. We had specific expectations for the type of galaxies that live in the early universe. They are young and small. Previous studies of the early universe with Hubble and other instruments tend to find small, blue baby galaxies at early times, objects which have just recently formed out of the primordial cosmic soup and are themselves building their early stars and structures. The most massive among these candidate galaxies had stellar masses estimated between 100 billion and 200 billion times the mass of our Sun. That's roughly comparable to the mass of the present-day Milky Way. The researchers found themselves looking at galaxy candidates as massive as our own galaxy, when the universe was only 3% of its current age. It was as if they'd discovered oak trees towering over a forest that had only existed for 3 weeks. The implications were staggering. If these observations held up under scrutiny, they suggested something fundamental was wrong with our understanding of how galaxies form. The standard model of cosmology, known as lambda CDM, which incorporates dark matter, dark energy, and normal matter, makes very specific predictions about how quickly structures can assemble in the early universe. This model had been spectacularly successful at explaining countless observations, from the cosmic microwave background radiation to the large-scale distribution of galaxies in the present-day universe. But it also sets firm limits on how fast galaxies can grow. Dark matter, the invisible substance that makes up about 27% of the universe's total mass energy content, provides the gravitational scaffolding on which galaxies form. After the Big Bang, tiny density fluctuations in the distribution of dark matter grew gradually under gravity's influence, forming dark matter halos, invisible gravitational wells into which normal matter could fall. These halos grew over time through mergers and by accreting more material. Only after dark matter halos reached certain sizes could they trap enough gas to ignite significant star formation. This process takes time. Dark matter doesn't collapse instantaneously into halos. Gas doesn't immediately cool and form stars. Each step has physical limits based on the laws of gravity, thermodynamics, and nuclear physics. When astronomers run computer simulations of galaxy formation, starting from the conditions of the early universe and evolving forward according to known physics, they can predict how many galaxies of various masses should exist at different cosmic epochs. These simulations had been refined over decades and cross-checked against countless observations. They worked, until James Webb looked at the cosmic dawn. The 6 massive galaxy candidates discovered in that first survey represented only the beginning. As Webb continued its observations, more and more similar objects appeared in the data. Other teams, analyzing different fields of the sky with Webb's cameras, began reporting their own discoveries of surprisingly massive and bright galaxies at extreme distances. By the end of 2022, astronomers had identified dozens of galaxy candidates that shouldn't exist according to standard theory. Some of these objects showed redshifts greater than 10, corresponding to times less than 500 million years after the Big Bang. One candidate, initially designated Glass Z13, appeared to exist just 300 million years after the Big Bang, making it potentially the earliest galaxy ever observed. Another, GNZ11, which had been identified earlier by Hubble but was now studied in detail by Webb, turned out to be not only incredibly distant, but also astonishingly bright and massive for its epoch. The astronomical community buzzed with excitement and concern. Conference presentations about Webb's early results drew standing-room-only crowds. Social media lit up with astronomers sharing the latest findings and debating their implications. Some researchers suggested the observations might herald a crisis for cosmology, potentially requiring modifications to the lambda CDM model that had served as the foundation for understanding the universe's evolution. Others urged caution, pointing out that the initial estimates of these galaxies' properties relied on photometric measurements, essentially educated guesses based on the galaxy's colors and brightness, rather than detailed spectroscopic observations that could provide definitive information about their distances and compositions. Leja emphasized this uncertainty. Another possibility is that these things are a different kind of weird object, such as faint quasars, which would be just as interesting. This qualifier was important. Photometric redshifts, while useful for initial surveys, can sometimes be dramatically wrong. A dust-obscured galaxy at a more moderate distance might appear red enough to be mistaken for an extremely distant galaxy. A bright quasar, powered by a supermassive black hole rather than by stars, might masquerade as a massive galaxy in broadband imaging. To resolve these questions, the teams needed follow-up observations with Webb's spectrographs, instruments that could split the light from these objects into spectra, showing the precise wavelengths of their emissions. Spectra would reveal telltale absorption and emission lines from specific elements, allowing precise distance measurements and providing detailed information about the physical conditions in these mysterious objects. But telescope time on Webb is precious and heavily oversubscribed. Getting spectroscopic confirmation for all the candidate galaxies would take years. In the meantime, the discoveries kept coming. The sheer number of massive galaxy candidates was itself a problem, even before considering the mass of individual objects. Theory predicted that such galaxies should be extremely rare in the early universe. Finding a handful would be remarkable, but Webb was finding them everywhere it looked, suggesting they might be hundreds of times more abundant than expected. This statistical excess was, in some ways, even more troubling than the existence of individual massive galaxies. One or two such objects might be explained as rare flukes, statistical outliers that beat the odds. But finding them in every deep field suggested something systematic was wrong with the Standard Model's predictions. Nelson and her colleagues had formed an ad hoc team specifically to investigate Webb's discoveries, bringing together experts from the United States, Australia, Denmark, and Spain. Their paper, published in the journal Nature in February 2023, presented 6 galaxy candidates with stellar masses estimated at several tens of billions of solar masses, existing just 500 to 700 million years after the Big Bang. The paper acknowledged the need for spectroscopic confirmation, but argued that even if only some of these candidates proved to be genuine, they would represent a significant challenge to galaxy formation theory. The discovery marked only the beginning of what would become a flood of unexpected findings from the James Webb Space Telescope, each one forcing astronomers to reconsider assumptions they'd held for decades about how the universe evolved from the smooth, nearly featureless state revealed by observations of the cosmic microwave background to the rich, structured cosmos we observe today. Understanding the early universe. To truly appreciate why these massive early galaxies represent such a profound mystery, we need to understand the story of the universe itself, from its explosive beginning to the formation of the first stars and galaxies. This is a story written in light and gravity, in the quantum fluctuations of the earliest moments and the patient accumulation of matter over billions of years. The universe began 13.8 billion years ago, in an event we call the Big Bang. This name, actually coined by a critic of the theory who thought it sounded absurd, has stuck despite being somewhat misleading. The Big Bang wasn't an explosion in space, but rather an explosion of space itself. Time and space came into existence together in that initial moment, and asking what came before the Big Bang may be as meaningless as asking what lies north of the North Pole. In its first moments, the universe was almost inconceivably hot and dense, so extreme that our usual understanding of physics breaks down. As space expanded and cooled, the universe went through a series of phase transitions, each one allowing new forms of matter and structure to emerge. Within the first second, quarks combined to form protons and neutrons. Within the first 3 minutes, these nuclear particles fused into the simplest atomic nuclei, primarily hydrogen and helium with trace amounts of lithium. But for nearly 400,000 years, the universe remained opaque, filled with a fog of ionized gas too hot for atoms to form. Photons of light couldn't travel far before being scattered by free electrons, creating a kind of cosmic smokescreen. Then, around 380,000 years after the Big Bang, the universe cooled enough for electrons to combine with nuclei, forming the first neutral atoms. This moment, called recombination, cleared the cosmic fog. Light could suddenly travel freely across space, and the universe became transparent. The photons, released at recombination, continue to fill the universe today, stretched by cosmic expansion into microwaves. We detect this cosmic microwave background radiation as a faint glow coming from all directions in the sky, always maintaining a temperature of about 2.7 degrees above absolute zero. Detailed maps of this radiation, created by satellites like the Wilkinson Microwave Anisotropy Probe and the Planck spacecraft, show it to be remarkably uniform, varying by only about 1 part in 100,000 across different regions of the sky. But those tiny variations are crucial. They represent the seeds of all future structure in the universe, density fluctuations that quantum mechanics generated during the first fraction of a second after the Big Bang, and that inflation, a brief period of exponential expansion, stretched to cosmic scales. In slightly denser regions, gravity pulled a bit more strongly, attracting additional matter. In slightly less dense regions, matter drifted toward the denser areas, leaving behind voids. This gravitational amplification continued through cosmic history, but it happened slowly at first. Visible matter, the ordinary atoms were made of, couldn't collapse efficiently immediately after recombination because radiation pressure and gas pressure resisted gravity's pull. Matter particles moving at high speeds don't clump together easily. Gas clouds that start to collapse heat up, generating outward pressure that opposes further collapse. Here's where dark matter becomes essential to the story. Dark matter, whatever it actually is, and we still don't know, doesn't interact with light or with itself except through gravity. It doesn't emit radiation, absorb radiation, or reflect radiation, which is why we call it dark. The only way we know it exists is through its gravitational effects on visible matter and on the path of light traveling through space. But these gravitational effects are profound. Observations of galaxy, rotation curves, gravitational lensing, the cosmic microwave background, and large-scale structure all point to the same conclusion. Dark matter outweighs visible matter by a factor of about 5 to 1. For every kilogram of ordinary atomic matter in the universe, there are approximately 5.4 kilograms of dark matter. This dark matter provides about 27% of the universe's total mass-energy content, compared to only about 5% for normal matter. Because dark matter doesn't interact with radiation, it could begin clumping together earlier and more efficiently than visible matter. Even before recombination, while visible matter was still coupled to radiation and couldn't collapse, dark matter was already collecting into dense halos under gravity's influence. These dark matter halos formed the gravitational scaffolding of the universe, invisible frameworks on which visible matter would later accumulate. After recombination, with radiation pressure no longer preventing its collapse, gas began falling into these dark matter halos. But even then, the process remained gradual. Gas, falling into a gravitational well, heats up through compression. This heat has to be radiated away before the gas can collapse further and become dense enough to form stars. In the densest central regions of the largest dark matter halos, gas eventually became concentrated enough and cool enough for gravity to overcome pressure, and stars began to ignite. This brings us to one of the most mysterious and exciting periods in cosmic history, the cosmic dawn. For hundreds of millions of years after recombination, the universe was dark, filled with neutral hydrogen gas but containing no stars, no galaxies, nothing that shone. Astronomers call this period the Cosmic Dark Ages, not because it was literally dark, since there were no eyes to see anything anyway, but because we have very little direct observational information about what happened during this time. Current theory and simulations suggest the first stars formed somewhere between 150 million and 400 million years after the Big Bang. These weren't stars like our Sun. They formed from primordial gas containing only hydrogen and helium, with none of the heavier elements that exist in modern stars. Computer models indicate these population 3 stars, as astronomers call them, would have been massive, perhaps 30 to 300 times the Sun's mass, and incredibly hot and bright, millions of times more luminous than the Sun. These first stars lived fast and died young, burning through their nuclear fuel in only a few million years before exploding as supernovae. But their deaths were as important as their lives. The supernova explosions forged heavier elements, carbon, oxygen, silicon, iron, all the elements that make planets and, eventually, life possible. These elements dispersed into the surrounding gas, enriching it and changing its properties. Gas, containing even trace amounts of elements heavier than helium, cools more efficiently, allowing smaller, longer-lived stars to form in subsequent generations. The first galaxies assembled from collections of these early stars and the dark matter halos hosting them. Initially, they were small, perhaps containing only a few million stars, irregular clumps without the graceful spiral or elliptical shapes we see in mature galaxies. These proto-galaxies merged with one another, growing gradually larger over hundreds of millions of years. According to the Standard Model, galaxy growth in the early universe proceeded hierarchically. Small structures formed first, then merged to create larger structures, which in turn merged to create still larger structures. This hierarchical assembly meant that truly massive galaxies, containing hundreds of billions of stars like the Milky Way, shouldn't appear until the universe had aged considerably, giving enough time for many smaller galaxies to find each other and merge. The cosmic web structure we observe in today's universe developed from the same process. Dark matter halos didn't form randomly scattered through space. They organized along filaments defined by the pattern of density fluctuations in the early universe. Where filaments intersected, especially dense concentrations of dark matter accumulated, eventually becoming the sites of galaxy clusters. Between the filaments lay vast voids, regions largely devoid of galaxies. Simulations of cosmic structure formation, running on supercomputers and following the gravitational evolution of billions of dark matter particles, beautifully reproduce the observed web-like pattern of galaxy distribution we see in the present-day universe. These simulations also make specific predictions about how many galaxies of various masses should exist at different cosmic times. The predictions depend on fundamental cosmological parameters like the density of dark matter, the expansion rate of the universe, and the amplitude of initial density fluctuations, all of which can be measured from observations of the cosmic microwave background. For decades, these simulations worked beautifully. The predicted number and properties of galaxies at various distances matched observations. When new, more powerful telescopes pushed observations to greater distances, looking at younger cosmic epochs, the agreement continued. Hubble's deep field observations revealed thousands of faint, distant galaxies existing 1 to 2 billion years after the Big Bang, and their properties matched theoretical expectations reasonably well. This success gave astronomers confidence in the Standard Model. Lambda CDM cosmology, incorporating dark matter and dark energy, seemed to work. We didn't know what dark matter was made of, and we had no idea what caused dark energy, but we could measure their effects and incorporate them into our models. The models made predictions that observations confirmed. Science was working as it should. Then James Webb opened its infrared eyes and looked at the cosmic dawn, and nothing was as it should have been. The galaxies Webb discovered were too big, too massive, too mature, and too abundant. They existed at times when simulations said such objects should be extraordinarily rare, if they existed at all. Something was wrong, either with the observations, with the theory, or with both. Why these galaxies shouldn't exist. The cosmic impossibility of these early massive galaxies becomes clear when we examine the fundamental limits physics imposes on how quickly galaxies can grow. This isn't merely about unexpected results or surprising measurements. It's about whether the known laws of nature can produce what Webb was seeing. Let's start with the most basic constraint: time. The galaxies identified by Labé's team existed just 500 to 700 million years after the Big Bang. This might sound like a long time, 500 million years, but in cosmic terms it's barely an eye blink. For comparison, our own Sun is about 4.6 billion years old. The entire span from the Big Bang to these massive galaxies is less than the current age of our star. During this brief cosmic interval, several things needed to happen in sequence. First, the initial density fluctuations had to grow under gravity until dark matter halos became massive enough to trap significant amounts of gas. This process can be calculated from the equations of gravitational collapse, and it sets a minimum time scale. You can't make dark matter halos collapse faster than gravity allows. Next, gas had to fall into these halos and cool enough to form stars. Gas falling into a gravitational well converts gravitational potential energy into thermal energy, heating up. Before stars can form, much of this heat must be radiated away. The cooling time depends on the gas density and composition. In the early universe, with gas composed almost entirely of hydrogen and helium, cooling was slower than in later epochs, when the trace amounts of heavier elements provided more efficient cooling channels. Then, stars had to form and live long enough to produce the stellar populations observed in these galaxies. Massive, hot stars might live only a few million years, but the red color of some early galaxies suggested the presence of older, cooler stars, which requires hundreds of millions of years to develop. The presence of red stars in galaxies that existed only 500 million years after the Big Bang implies star formation must have begun even earlier, perhaps only 100 to 200 million years after the Big Bang, barely enough time for the first dark matter halos to have assembled. But the problem goes deeper than just timing. It's also about mass budgets. The total mass that could have collapsed into a galaxy depends on the mass of its dark matter halo, and the mass of dark matter halos is set by the growth of density fluctuations. The lambda CDM model makes very specific predictions about the distribution of dark matter halo masses at any given time in cosmic history. These predictions have been tested extensively at later times and found to be highly accurate. When researchers extended these predictions back to the cosmic dawn, 500 to 700 million years after the Big Bang, they found that dark matter halos massive, enough to host galaxies with hundreds of billions of stars, should be extraordinarily rare. We're talking about statistics here. The theory doesn't say such halos can't exist, only that they should be extremely uncommon in any given volume of space. Finding even one in a small survey area would be notable, but Webb was finding them routinely in every deep field observed. Michael Boylan Colchin, an astrophysicist at the University of Texas at Austin, created what became known as the impossibility diagram, plotting the maximum possible stellar mass for galaxies at different redshifts against what the lambda CDM model predicts. The most massive galaxy candidates from Webb's observations sat right at or beyond the edge of theoretical possibility. They were pushing or exceeding the absolute maximum mass that could exist given the available reservoir of collapsed dark matter at those early times. This led to what some researchers began calling the mass budget problem. Even if you assumed absolutely optimal conditions, perfectly efficient conversion of gas into stars, no losses to outflows or other processes, the amount of available gas in the most massive dark matter halos of that era barely sufficed to create the stellar masses Webb was measuring. And real galaxy formation is never perfectly efficient. Significant amounts of gas get expelled by stellar winds and supernova explosions, blown out of galaxies before they can form stars. Modern galaxies typically convert only about 10 to 20% of their available gas into stars over their lifetimes. The remaining 80 to 90% either stays as gas, gets blown out by energetic processes, or never falls into the galaxy in the first place. For the early galaxies Webb discovered to achieve their observed stellar masses, they would need to convert gas into stars with efficiencies approaching 100%, every atom of available gas becoming part of a star. This seems physically implausible, given what we understand about the feedback processes that regulate star formation. Then there's the maturity problem. Several of Webb's discovered galaxies didn't just have large stellar masses. They also showed red colors indicating the presence of older stellar populations. Stars shine blue when they're young and hot, burning their nuclear fuel at prodigious rates. As stars age and exhaust their core hydrogen, they swell into red giants, becoming cooler but larger. The reddest stars in a galaxy are typically the oldest. In the present-day universe, red galaxies are usually massive elliptical galaxies that exhausted most of their gas billions of years ago, and now contain primarily old stars, the stellar populations formed long ago now aging and cooling. Finding red galaxies in the cosmic dawn was like discovering retirees in a kindergarten classroom. How could galaxies develop old stellar populations when the universe itself was still in its infancy? The issue isn't just that old. Stars exist. Any star that forms is old to the extent it's lived some portion of its lifetime. But that these red colors suggested stars that had been burning for substantial fractions of the universe's age at that time. If a galaxy observed 500 million years after the Big Bang contains stars that are already 300 million years old, those stars must have formed just 200 million years after the Big Bang, at the very earliest possible moment star formation could begin. This compression of timelines creates cascading problems. It means the dark matter halos, the gas cooling, the first stars, and the assembly of enough stellar mass to create a massive red galaxy all had to happen with essentially no wasted time, each process occurring at its maximum possible speed. There's no room for the gradual hierarchical assembly that simulations predict. Everything had to happen at once, right at the cosmic dawn, almost as if someone had pressed a fast-forward button on galaxy formation. Some researchers began exploring whether the lambda CDM model itself might need revision. Perhaps the amplitude of density fluctuations in the early universe was higher than measurements of the cosmic microwave background suggest, allowing more massive dark matter halos to form earlier. But changing this parameter to accommodate Webb's galaxies would throw off other predictions that match observations beautifully, like the distribution of galaxy clusters in the present-day universe. Others suggested modifications to dark energy, proposing something called early dark energy that might have existed in the first billion years after the Big Bang before decaying away. This early dark energy could potentially alter the growth rate of cosmic structures during the critical period when these massive galaxies formed. But early dark energy was already a speculative concept proposed to address other cosmological tensions, and invoking it to explain Webb's observations without independent evidence felt like adding epicycles to save a theory. Meanwhile, the discoveries continued accelerating. In September 2023, another team announced finding thousands of disk galaxies like the Milky Way in the early universe, many of them existing when the universe was just a few billion years old. These structured galaxies, with their organized spiral arms and rotating disks, were thought to form through gentle processes over many billions of years. Finding them already in place in the young universe suggested that galactic structure developed far more quickly than anyone expected. Then came the red monsters, a name that perfectly captured both the color and the threatening implications of these objects for standard cosmology. Announced in November 2024, these three extremely massive and dusty galaxies existed within the first billion years after the Big Bang and were forming stars nearly twice as efficiently as galaxies at later times. They defied not just mass, predictions, but also our understanding of star formation physics. Conventional models suggested that only about 20% of gas in a galaxy should convert into stars, with the rest either remaining as gas or being expelled by stellar feedback. The red monsters appeared to be converting gas into stars at 40% efficiency or more, doubling the expected rate. If this was real, it meant something fundamental about star formation worked differently in the early universe. Each new discovery added weight to the problem. These weren't isolated anomalies or individual outliers. Webb was revealing an entire population of galaxies that shouldn't exist according to our best theories. The universe at cosmic dawn was far more evolved, far more structured, and far more productive at making galaxies than decades of theoretical work had predicted it should be. The red monsters and little red dots. As James Webb continued its survey of the early universe throughout 2023 and 2024, a peculiar pattern emerged in the data. Among the thousands of galaxies discovered at high redshifts, certain objects stood out for their distinctive appearance. They glowed brilliantly red in Webb's infrared images, earning them colorful nicknames that reflected both their appearance and the challenge they posed to astronomers. The red monsters, discovered by a team led by Mengyuan Xiao of the University of Geneva, represented perhaps the most extreme examples of this phenomenon. These three galaxies existed when the universe was between 600 million and 1 billion years old, making them contemporaries of the impossible galaxies discovered by Lebes's team. But what made the red monsters particularly monstrous was their combination of properties: tremendous mass, intense star formation, and remarkable efficiency at converting gas into stars. Using Webb's near-infrared camera and its GRISM spectrograph capability, Xiao's team measured detailed spectra of these objects, allowing precise determinations of their distances, stellar masses, and star formation rates. The results were striking. Each red monster contained stellar mass approaching or exceeding 100 billion times the mass of the Sun, comparable to massive galaxies in the present-day universe. Yet they existed at a cosmic epoch when such massive galaxies should have been extraordinarily rare, if they existed at all. The spectra revealed something even more surprising. These galaxies weren't just massive. They were actively forming new stars at prodigious rates, creating hundreds of new suns every year. For comparison, the Milky Way currently forms about 2 new stars per year. The red monsters were outproducing our galaxy by a factor of 100 or more, despite existing when the universe was less than a tenth its current age. But the truly shocking discovery came when the team calculated the star formation efficiency, the fraction of available gas that was being converted into stars. In modern galaxies, various feedback processes regulate star formation, preventing it from becoming too efficient. Stellar winds from massive young stars blow gas out of star-forming regions. Supernova explosions shock and heat surrounding gas, temporarily halting its collapse. Radiation pressure from intense starlight pushes in infalling gas clouds. All these processes combine to limit star formation efficiency to typically 20% or less. The red monsters appeared to be forming stars with efficiencies approaching 40%, nearly double the expected rate. It was as if someone had turned off the regulatory mechanisms that normally prevent galaxies from converting all their gas into stars too quickly. The implications were profound. Either star formation physics worked fundamentally differently in the early universe, or our understanding of feedback processes was incomplete. What made these galaxies so red? The color came primarily from dust. Dust, in astronomical terminology, doesn't mean household dust, but rather microscopic grains of solid material, primarily silicates and carbon compounds mixed with the gas between stars. Dust absorbs and scatters light, and it absorbs blue light more effectively than red light, making dust-enshrouded objects appear redder than they actually are. The presence of substantial dust in these early galaxies was itself somewhat surprising. Dust forms from elements heavier than hydrogen and helium, elements that can only be created inside stars and dispersed by supernova explosions. In the very early universe, with only 1 or 2 generations of stars having formed and died, one might expect relatively little dust. Yet the red monsters showed signs of being heavily dust-obscured, suggesting they'd already cycled through enough stellar generations to produce substantial quantities of heavy elements. The red monsters weren't alone in exhibiting peculiar red colors. Throughout 2023 and 2024, Webb discovered numerous other red objects in the early universe, collectively nicknamed little red dots, for their compact, point-like appearance and crimson hue in infrared images. These little red dots presented their own mysteries, objects that didn't quite fit into any established category of cosmic structures. Initial observations suggested the little red dots might be extremely distant galaxies, similar to the red monsters, but smaller and more compact. Their red colors could be explained by dust obscuration or by old stellar populations. But as spectroscopic follow-up observations accumulated, a more complex picture emerged. Many little red dots showed spectral features characteristic of active galactic nuclei, extremely luminous sources of radiation powered by supermassive black holes at the centers of galaxies. The discovery that many little red dots harbored active black holes added another layer to the early universe puzzle. Supermassive black holes, objects containing millions or billions of times the mass of the Sun, exist at the centers of most large galaxies in the present-day universe, including our own Milky Way. But how these massive black holes formed remains one of astronomy's outstanding questions, and finding them already in place in the cosmic dawn only deepens the mystery. Black holes grow by accreting matter, pulling in gas and occasionally other stars or even other black holes. But there are limits to how fast they can grow. When matter falls onto a black hole, it heats up and emits radiation. This radiation exerts outward pressure on additional infalling material, creating a natural limit called the Eddington limit. A black hole accreting at the Eddington limit can roughly double its mass every 50 million years or so. Starting from stellar mass black holes, formed from the collapse of massive stars and weighing perhaps 10 to 100 times the mass of the Sun, and growing at the Eddington limit, black holes could theoretically reach millions of solar masses within hundreds of millions of years. But the massive black holes Webb discovered in little red dots appeared to weigh billions of solar masses despite existing only 600 to 800 million years after the Big Bang. The math doesn't quite work. To grow from stellar mass seeds to billions of solar masses in the available time requires either starting from much more massive seeds, somehow forming black holes weighing hundreds of thousands of solar masses from the beginning, or growing faster than the Eddington limit predicts. Both scenarios push the boundaries of our understanding. The seed question has long vexed theorists. How do supermassive black holes get started? One possibility is that the first generation of massive stars collapsed directly into black holes, weighing tens to hundreds of solar masses. These light seed black holes could then grow through accretion and mergers. Another idea involves heavy seeds, forming when massive gas clouds collapse directly into black holes without first forming stars, potentially creating objects weighing 100,000 solar masses or more from the start. Webb's discoveries of massive black holes in the cosmic dawn seem to favor the heavy seed scenario, or at least suggest that light seeds alone can't explain the observations. But heavy seeds require special conditions to form, conditions that might be rare in the early universe. And yet, Webb was finding little red dots everywhere, suggesting that if they all contained supermassive black holes, such objects were common, not rare. Some little red dots showed another puzzling characteristic. They appeared to be accreting matter at rates exceeding the Eddington limit, sometimes by factors of 10 or more. This super-Eddington accretion had been theoretically predicted but rarely observed. Finding it common in the early universe suggested that young black holes could indeed grow faster than the Eddington limit indicates, at least temporarily, providing a possible solution to the mass growth problem. The red color of these accreting black holes likely comes from dust in the surrounding material. As gas spirals into a black hole, Forming an accretion disk, it heats up and emits copious ultraviolet and X-ray radiation. This energetic radiation can create dust in the surrounding environment or heat existing dust, causing it to glow in the infrared part of the spectrum that Webb detects. Researchers found that in many cases, what appeared to be a massive galaxy in initial photometric observations was actually a much smaller galaxy, hosting an extraordinarily bright and massive black hole. The intense radiation from the accreting black hole outshone the stars in the galaxy, making the whole system appear brighter and more massive than the galaxy itself actually was. This discovery provided some relief to theorists, suggesting that at least some of the mass budget problem might be solved by recognizing that black holes, not just stars, contribute to the observed brightness. But this solution came with its own problems. If little red dots are primarily powered by massive black holes rather than stars, where did the black holes come from? How did they grow so massive so quickly? And why are they so common in the early universe? The discovery of one type of impossible object, massive early galaxies, had led to the discovery of another type of impossible object, massive early black holes. Throughout 2024, spectroscopic confirmation campaigns targeted hundreds of high redshift galaxy candidates, attempting to measure precise distances and determine whether these objects were truly as massive and distant as photometric estimates suggested. Some candidates turned out to be less distant than initially thought, their red colors explained by dust rather than cosmic expansion. These interlopers were actually galaxies at more moderate distances that happened to appear red. But many candidates confirmed as genuine, existing at the extreme distances and early times indicated by their colors. The confirmation rate varied among different surveys and selection techniques, but overall, a substantial fraction of the mysterious red objects turned out to be exactly as distant and problematic as they first appeared. The red monsters and little red dots revealed something profound about the cosmic dawn. The early universe wasn't a simple, uniform expanse of small, primitive proto-galaxies gradually assembling into larger structures. Instead, it was already a diverse cosmic ecosystem, containing a surprising variety of objects, massive, dusty galaxies forming stars at extraordinary rates, compact galaxies hosting enormous black holes, structured disk galaxies with organized rotation, and, yes, also the small, blue, star-forming galaxies that theory had predicted. This diversity posed its own challenge to theorists. If the early universe could produce such a wide range of galaxy types and masses, what physical processes were responsible? Why did some gas clouds become massive red monsters, while others became little red dots? What determined which dark matter halos would host quietly star-forming galaxies, and which would harbor supermassive black holes? Black holes in the cosmic dawn. Among all of Webb's startling discoveries about the early universe, perhaps none proved more puzzling than its revelations about supermassive black holes. These gravitational monsters, containing millions or billions of times the Sun's mass, appeared already fully formed when the universe was barely out of its infancy, raising fundamental questions about how such extreme objects could exist so early in cosmic history. In March 2024, Nature published a paper describing the discovery of a supermassive black hole in a galaxy designated GN-Z11, observed as it existed just 430 million years after the Big Bang. This wasn't merely a massive black hole. It was actively feeding, pulling in matter at a furious rate and radiating enormous amounts of energy across the electromagnetic spectrum. Detailed spectroscopic analysis revealed high-velocity gas swirling around the black hole, heated to millions of degrees by the accretion process. But what made this discovery particularly significant was the ratio between the black hole's mass and the mass of stars in the host galaxy. In the present-day universe, astronomers have observed a tight relationship between central black hole mass and galaxy stellar mass, with the black hole typically containing about 0.1% of the galaxy's total stellar mass. This relationship suggests that black holes and their host galaxies grow together through cosmic history, their evolution intimately connected. GNZ11's black hole appeared to violate this relationship dramatically. Measurements suggested the black hole might contain 2 million times the mass of the Sun, while residing in a galaxy containing only about 1 billion solar masses worth of stars. That means the black hole represented roughly 0.2% of the galaxy's stellar mass, about 20 times higher than the typical ratio in modern galaxies. The black hole was abnormally massive for its galaxy, suggesting it had grown faster than the galaxy itself could form stars. This pattern repeated in other early galaxies Webb discovered. Many showed black hole to stellar mass ratios, far exceeding what's observed in the present-day universe. Some objects, particularly among the little red dots, appeared to have black holes containing 10, 20, or even 30% of the total stellar mass of their host galaxies. These top-heavy systems seemed fundamentally different from galaxies in the modern universe. The implications were profound. The tight relationship between black hole and galaxy mass in the present-day universe had led astronomers to conclude that black holes and galaxies co-evolve, influencing each other's growth through cosmic history. Energetic outflows from actively accreting black holes, called active galactic nuclei feedback, can heat gas in the surrounding galaxy, temporarily shutting down star formation and regulating both the black hole's growth and the galaxy's stellar mass. But if early black holes grew much faster than their host galaxies, this coevolution might not have operated in the cosmic dawn. Perhaps black holes formed first and grew rapidly, with their host galaxies catching up later. Or perhaps the feedback processes that regulate black hole growth in modern galaxies worked differently or less efficiently in the early universe, allowing black holes to grow to larger masses before feedback kicked in to slow their growth. The discovery that shook the astronomical community came in November 2024, when a team led by Haiyuan Su from the International Gemini Observatory announced finding a supermassive black hole designated LID 568, observed just 1.5 billion years after the Big Bang, feeding at a rate more than 40 times the theoretical Eddington limit. This was super-Eddington accretion taken to an extreme. The Eddington limit, calculated from the balance between radiation pressure pushing outward and gravity pulling inward, sets what? Astronomers had long considered a firm ceiling on how fast black holes could grow. Exceed this limit, and radiation pressure should blow away the infouling matter before it reaches the black hole. Yet, LID 568 appeared to be gleefully ignoring this supposed limit, gorging on matter at a rate that should be physically impossible. The discovery suggested that black holes in the early universe might regularly experience brief episodes of super-Eddington accretion, perhaps triggered by galaxy mergers that dumped enormous quantities of gas onto the black hole in a short time. If such feeding frenzies occurred, they could allow black holes to grow much faster than previously thought possible, potentially explaining how they reached billions of solar masses within the first billion years. However, this discovery soon became embroiled in controversy. In April 2025, another team reanalyzed the same observations and found that the extreme accretion rate was likely an overestimate. The black hole sat in a very dusty environment, and the dust had absorbed much of the black hole's radiation before it could reach Webb's instruments. When properly correcting for this dust extinction, the apparent super-Eddington accretion rate dropped to something more consistent with the Eddington limit. This correction was important because it showed how challenging it is to accurately measure properties of objects in the dusty early universe. Dust doesn't just make things appear redder, it also makes them appear dimmer by absorbing their light. If you don't correctly account for this dimming, you might underestimate how luminous an object truly is. But measuring the amount of dust obscuration is itself difficult, particularly in the complex environments around actively accreting black holes. The LID 568 saga illustrated a broader point about Webb's discoveries. Many of the most extreme initial results, the largest masses, the highest accretion rates, the most severe violations of theoretical limits were based on preliminary analyses that made various assumptions about dust content, stellar populations, and other factors. As more detailed spectroscopic data became available and researchers refined their analysis techniques, some extreme values moderated toward more conventional ranges. But even with these corrections, the basic problem remained. Supermassive black holes existed in the cosmic dawn, and they were more massive and more common than theory predicted they should be. Whether they grew at exactly the Eddington limit or somewhat faster didn't change the fundamental puzzle of where they came from and how they grew so large so fast. In June 2024, Webb discovered another remarkable phenomenon. Two supermassive black holes in the process of merging, observed when the universe was just 740 million years old. The system showed clear spectroscopic signatures of two distinct black holes, each weighing approximately 50 million times the Sun's mass, orbiting each other and apparently on a collision course. Black hole mergers had been predicted to be important for building up supermassive black holes. When two galaxies merge, their central black holes eventually sink to the center of the merged galaxy and form a binary pair. Over time, gravitational interactions with surrounding stars and gas carry away orbital energy, causing the black holes to spiral closer together. Eventually, when they get close enough, gravitational wave emission dominates, and the black holes rapidly merge into a single, more massive black hole. Finding such a merger already in progress at cosmic dawn suggested this process was operating very early. But it also raised questions. For two supermassive black holes to merge, two galaxies must have merged first, meaning both galaxies must have formed earlier still and grown their own central black holes. The timeline compression continues getting pushed to earlier and earlier times. The merger discovery also excited gravitational wave astronomers. When black holes merge, they emit gravitational waves, ripples in the fabric of space-time itself. Ground-based gravitational wave detectors like LIGO and Virgo have successfully detected mergers of stellar mass black holes, objects weighing a few tens of solar masses. But supermassive black hole mergers produce gravitational waves at much lower frequencies that ground-based detectors can't sense. The planned space-based laser interferometer space antenna, LISA, approved by the European Space Agency and scheduled for launch in the 2030s, will specifically target gravitational waves from supermassive black hole mergers. Webb's discovery of early mergers provides an estimate of how common such events might be and what signals LISA might detect. When LISA begins operations, it might directly observe the gravitational waves from supermassive black hole mergers in the cosmic dawn, providing an entirely independent way to study these objects and their growth. Throughout 2024 and into 2025, the picture of early black holes became increasingly complex. Some objects showed clear signs of rapid growth through super-Eddington accretion. Others appeared to have formed from heavy seeds, starting with larger initial masses. Some resided in relatively small galaxies, while others occupied what appeared to be more massive systems. The diversity suggested multiple pathways for supermassive black hole formation might operate simultaneously in the early universe. One intriguing possibility involved primordial black holes, hypothetical objects that might have formed directly from density fluctuations in the first moments after the Big Bang, long before any stars existed. These primordial black holes could range in mass from microscopic to millions of solar masses. If substantial populations of massive primordial black holes existed, they could provide ready-made seeds for supermassive black holes, eliminating the need for black holes to grow from stellar mass origins. The idea of primordial black holes isn't new. It's been proposed as a possible component of dark matter. But Webb's discoveries renewed interest in the concept as a possible solution to the supermassive black hole formation problem. If primordial black holes existed and had the right mass distribution, they could explain both how supermassive black holes got started and potentially contribute to the dark matter that shapes cosmic structure. However, various astronomical observations constrain how many primordial black holes could exist at different mass ranges. Too many, and they would have observable effects that we don't see. The parameter space for primordial black holes as dark matter has been steadily shrinking as observations improve. Using them to explain early supermassive black holes would require they exist in precisely the right mass range and abundance, which many theorists find somewhat contrived. The black hole puzzle highlighted a fundamental tension in understanding the cosmic dawn. On one hand, finding massive black holes so early suggests the universe's youth was far more complex and productive than we thought. On the other hand, these discoveries push toward ever more exotic explanations: super-Eddington accretion, heavy seeds, primordial black holes, and modifications to cosmology. Finding the right balance between accepting genuinely new physics and recognizing that observational uncertainties and systematic effects might explain some anomalies remains an ongoing challenge. Possible explanations. As the wealth of Webb discoveries accumulated through 2023, 2024, and into 2025, astronomers began exploring various explanations for the apparent impossibilities piling up in the cosmic dawn. Some proposals focused on astrophysical solutions, ways that galaxy formation and black hole growth might operate differently in the early universe without requiring changes to fundamental cosmology. Others suggested more radical revisions to our understanding of the universe itself. One of the earliest and most straightforward explanations centered on active galactic nuclei. Many of the massive, bright objects Webb discovered might not be dominated by starlight at all. Instead, they could be relatively smaller galaxies hosting extremely luminous supermassive black holes whose radiation outshines the entire stellar population. This wouldn't solve the black hole formation problem, but it would alleviate the impossible galaxy mass problem by revealing that some, apparently, massive galaxies weren't actually as massive as they seemed. This AGN contamination hypothesis gained support as spectroscopic observations accumulated. Numerous objects initially classified as massive, star-forming galaxies turned out, upon closer examination, to show spectral signatures characteristic of active black holes. Broad emission lines from gas swirling at high velocities, high ionization emission lines from gas heated by intense radiation, and X-ray emission from the hot accretion disk. In November 2024, a study by Catherine Chworowski and colleagues at the University of Texas at Austin provided systematic evidence for AGN contamination. By carefully analyzing Webb spectroscopy of early galaxy candidates, they demonstrated that black holes contributed significantly to the observed light in many cases. When they subtracted the AGN contribution and recalculated stellar masses, some galaxies dropped from seemingly impossible masses to more reasonable values consistent with theoretical predictions. Stephen Finkelstein, a co-author on the study, stated the implications clearly. So, the bottom line is there is no crisis in terms of the standard model of cosmology. Any time you have a theory that has stood the test of time for so long, you have to have overwhelming evidence to really throw it out. And that's simply not the case. This was welcome news for cosmologists who had grown concerned about whether lambda CDM could survive Webb's onslaught. But Chworowski's study didn't eliminate all anomalies. Even after accounting for AGN contamination, Webb observations still revealed approximately twice as many massive galaxies in the early universe as standard models predicted. The problem was reduced but not solved. This remaining excess prompted researchers to consider modifications to star formation physics. Perhaps stars formed more efficiently in the early universe than at later times. In the present-day universe, only about 10 to 20% of gas in galaxies converts into stars. The remaining gas either stays as gas, gets expelled by stellar winds and supernovae, or never falls into the galaxy. This low efficiency results from various feedback processes that regulate star formation. But conditions in the early universe differed significantly from today. Gas was almost entirely hydrogen and helium, with virtually no heavier elements. This primordial composition affects how gas cools, how it fragments into star-forming clumps, and how radiation from young stars interacts with surrounding gas. Computer simulations suggested that under these conditions, star formation might proceed more efficiently, perhaps converting 30 or 40% of gas into stars rather than 10 to 20%. The red monsters provided evidence supporting this idea. Their apparent star formation efficiencies, approaching 40% or more, suggested that at least some early galaxies did convert gas into stars more efficiently than modern galaxies. If this was common rather than exceptional, it could help explain why early galaxies appear more massive than expected without requiring them to contain unreasonably large amounts of gas. Another possibility involved bursty star formation. Rather than forming stars at a steady, continuous rate like the Milky Way does today, early galaxies might undergo intense episodes of star formation separated by quieter periods. During a burst, a galaxy might form hundreds or thousands of solar masses worth of stars per year, far exceeding its average rate. If Webb happened to catch many early galaxies during such bursts, they would appear unusually bright and star-forming, creating an excess of apparently massive galaxies. Simulations of early galaxy evolution suggested that bursty star formation should indeed be common. Small galaxies with relatively shallow gravitational potential wells might struggle to retain gas after intense star formation heats and stirs the interstellar medium. Gas expelled during a starburst might take tens or hundreds of millions of years to cool and fall back into the galaxy, triggering the next burst. This cycle could make early galaxies highly variable, with their apparent properties depending strongly on when you observe them. If most early galaxies go through intense starbursts, a snapshot survey like Webb's early release science observations would preferentially find galaxies during or shortly after bursts, when they're brightest. Quieter galaxies between bursts might be too faint to detect, creating a selection bias toward bright, apparently massive systems. This observational bias could make massive galaxies appear more common than they really are. Some researchers proposed that the initial mass function, the distribution of masses for newly formed stars, might differ in the early universe. In the present-day universe, star formation produces many low-mass stars and relatively few high-mass stars. Specifically, for every star weighing 20 times the Sun's mass, you might form hundreds of stars weighing 1 solar mass and thousands of stars weighing 0.1 solar masses. But high-mass stars are far more luminous than low-mass stars. A 20 solar mass star shines about 10,000 times brighter than the Sun, while a 0.1 solar mass star shines about 100 times dimmer. If the early universe produced a higher proportion of massive stars, the same total stellar mass would appear much brighter. This top-heavy initial mass function could make early galaxies seem more massive than they actually are when mass estimates are based on their luminosity. Population 3 stars, the first generation formed from primordial gas, were likely more massive on average than stars forming today. Computer simulations suggested they typically weighed tens to hundreds of solar masses. But population 3 stars should be extremely rare in most early galaxies, which would have cycled through at least 1 or 2 stellar generations by the time Webb observes them, producing small amounts of heavier elements that change cooling physics and allow smaller stars to form. Still, even small populations of population 3 stars, or similarly massive stars, could contribute disproportionately to a galaxy's luminosity. Some researchers suggested that early galaxies might have prolonged population 3 star formation, or produce unusually large numbers of massive stars even in later generations, potentially explaining their excess brightness. Dust extinction presented another source of uncertainty in mass estimates. Dust absorbs and scatters light, making dusty galaxies appear dimmer than they actually are. If you don't correctly account for dust when estimating a galaxy's mass from its observed brightness, you'll underestimate the mass. This works in the opposite direction from the AGN contamination problem, where extra light from black holes can make galaxies appear more massive than they are. Different galaxies contain different amounts of dust, and the geometry of dust distribution matters too. Edge-on spiral galaxies, viewed through their dust lanes, appear much dimmer than face-on spirals of the same mass. Without detailed information about dust content and viewing geometry, individual mass estimates can be uncertain by factors of 2 or 3. For the dusty red monsters, properly accounting for dust extinction increased estimated stellar masses rather than decreasing them. Researchers had to infer how much light was being absorbed by dust and add that back in when calculating the total star formation rate and stellar mass. But the amount of dust in early galaxies was itself uncertain. Dust forms from elements heavier than helium, created in stars and dispersed by supernovae. The early universe, with few stellar generations completed, should contain less dust than galaxies at later times. Yet some early galaxies appeared heavily dust-obscured. This apparent abundance of dust itself posed a puzzle. Where did all the dust come from so quickly? Perhaps the first generations of massive stars produced and dispersed heavy elements more efficiently than thought. Or perhaps dust formation processes worked differently in the metal-poor gas of early galaxies, allowing substantial dust masses to form from small amounts of heavy elements. More radical proposals invoked modifications to cosmology itself. One approach suggested varying the fundamental constants of nature. If physical constants like the gravitational constant or the speed of light weren't actually constant, but instead changed over cosmic time, this could alter the universe's expansion history and structure formation timeline. Rajendra Gupta, a physicist at the University of Ottawa, proposed a model combining tired light concepts, an old alternative to cosmic expansion, with varying fundamental constants to extend the universe's effective age at early times. In this covarying coupling constants model, the universe would be about 27 billion years old rather than 13.8 billion years, providing much more time for early structure formation. At a redshift of 10, corresponding to about 430 million years after the Big Bang in standard cosmology, Gupta's model would allow nearly 6 billion years of cosmic time, plenty for massive galaxies to form. This would neatly solve the time crunch problem. However, the model faces significant challenges. It struggles to explain the cosmic microwave background radiation's isotropy and other observations that standard cosmology handles well. Most cosmologists remain skeptical, viewing the model as too contrived and incompatible with too much observational evidence. Another cosmological proposal involved early dark energy, a hypothetical energy component that might have existed in the first billion years of cosmic history before decaying away. This early dark energy could affect the growth rate of density, fluctuations during the crucial period when the first structures formed, potentially allowing more massive dark matter halos to assemble earlier than standard cosmology predicts. Early dark energy has been proposed as a possible solution to the Hubble tension, a discrepancy between different measurements of the universe's current expansion rate. If the same physics that resolves the Hubble tension also helps explain Webb's early galaxies, it would provide multiple independent pieces of evidence pointing toward the same new physics. However, current models of early dark energy don't fully resolve Webb's observations without fine-tuning, and the connection between the Hubble tension and early structure formation remains uncertain. A 2025 paper by Christos Tsagas proposed an intriguing solution that operates within standard general relativity without invoking new physics. The idea centers on peculiar velocities, the random motions of matter relative to the smooth cosmic expansion. In standard cosmological calculations, these peculiar motions are usually treated as small perturbations that don't significantly affect structure formation. But Tsagas argued that in general relativity, unlike Newtonian gravity, energy flux from moving matter gravitates, contributing to the gravitational field. This relativistic effect of peculiar velocities could, according to Tsagas, expedite structure formation in the early universe, allowing massive galaxies to form earlier than standard calculations predict. The proposal had the advantage of not requiring any new physics beyond general relativity, and not invoking primordial black holes, modified power spectra, or super-Eddington accretion. However, the magnitude of the effect and whether it truly solves the early galaxy problem remained subjects of ongoing research and debate. As research continued, a consensus emerged that the solution likely involved multiple factors rather than a single explanation. Some apparently massive galaxies were indeed AGN-dominated and not as stellar mass-rich as they appeared. Some galaxies formed stars more efficiently or more burstily than modern galaxies. Some mass estimates were affected by dust extinction or uncertain initial mass functions. And perhaps some modification to either astrophysics or cosmology was also necessary to fully explain all observations. The key would be continuing to accumulate high-quality spectroscopic data, refining theoretical models, and maintaining healthy skepticism about both the most extreme observational claims and the most exotic theoretical proposals. What this means for our understanding. The discoveries made by the James Webb Space Telescope in its first 3 years of operation represent more than just individual anomalies or corrections to astronomical catalogs. They signal a fundamental shift in how we understand the universe's earliest epochs and raise profound questions about whether our current cosmological model captures the full story of cosmic evolution. At its core, the challenge Webb poses to cosmology comes down to a simple question. Can the lambda CDM model, which successfully explains the cosmic microwave background, the large-scale distribution of galaxies in the present-day universe, and countless other observations, also account for what we see at the cosmic dawn? Or does something need to change? The lambda CDM model rests on several key components. Lambda represents dark energy, the mysterious influence driving the universe's accelerated expansion. CDM stands for cold, dark matter, the invisible substance that provides gravitational scaffolding for cosmic structure. The model also includes ordinary matter, baryons, radiation, and specifies the geometry and expansion history of the universe. Crucially, the model makes precise predictions about how structure grows over cosmic time, starting from the tiny density fluctuations visible in the cosmic microwave background and ending with the rich structure of galaxies and clusters we observe today. For more than 2 decades, lambda CDM has passed test after test. Observations of distant supernovae confirmed cosmic acceleration. Detailed measurements of the cosmic microwave background by satellites like Planck determined cosmological parameters to percent-level precision. Large galaxy surveys mapped the universe's structure, and the observed patterns matched simulations based on lambda CDM. The success was so thorough that cosmology transformed from a field rife with competing models to one with a standard model that almost everyone accepted. Webb's discoveries don't obviously break lambda CDM, at least not yet. The model makes probabilistic predictions rather than absolute statements. It says massive galaxies should be rare at early times, not impossible. Finding a few such galaxies represents an unlikely but not forbidden outcome. The question is, how unlikely? If Webb's observations represent a 1 in 1,000 statistical fluke, they're interesting but not deeply concerning. If they represent something that should happen only once in a million random universes, according to lambda CDM, they suggest the model needs revision. Michael Boylan-Kolchin's impossibility diagram placed the most massive early galaxies right at the edge of what lambda CDM allows. They weren't comfortably inside the predicted range, but they weren't impossibly beyond it either. Subsequent refinements, particularly recognizing AGN contamination in some objects, pulled some galaxies back from the edge. But a population of unexpectedly massive and abundant early galaxies remained even in the most conservative analyses. This presents cosmologists with a choice. They can maintain lambda CDM and explain the early galaxies through astrophysical processes within the model's framework. Perhaps star formation efficiency was higher, stellar populations different, or selection biases stronger than recognized. These solutions preserve the cosmological model while adjusting our understanding of how galaxies form. Alternatively, they can consider that lambda CDM might need modification, perhaps through early dark energy, varying fundamental constants, or other extensions that alter structure formation predictions at early times. The conservative approach favors astrophysical solutions for good reason. Lambda CDM didn't become the standard model by accident. It earned that status through decades of successful predictions. Extraordinary claims, like the need to revise the standard model, require extraordinary evidence. And the evidence from Webb, while surprising, hasn't yet reached the extraordinary threshold that would compel most cosmologists to abandon lambda CDM. But neither can astronomers simply dismiss Webb's observations as measurement errors or selection effects. Multiple independent teams using different analysis techniques have found similar patterns. The number of massive galaxies exceeds predictions. The presence of supermassive black holes at early times strains conventional growth scenarios. The existence of mature, dusty galaxies when the universe was barely 500 million years old compresses timelines uncomfortably. Katie Mack, a theoretical astrophysicist and Hawking Chair in Cosmology and Science Communication at the Perimeter Institute for Theoretical Physics, offered a measured perspective in a 2023 article. Just like your amazingly productive office mate, what looks utterly impossible to us might be less about altering physical laws and more about using the time we have incredibly efficiently. This analogy captures an important insight. When confronted with galaxies that seem impossibly massive for their age, we must ask whether the problem lies in what's possible or in what we expected. Perhaps the early universe was simply more efficient at forming structures than our models predicted, not because physics was different, but because we didn't fully understand how existing physics operates under early universe conditions. The Hubble tension provides an instructive parallel. For several years, astronomers have grappled with the discrepancy between two ways of measuring the universe's current expansion rate. Observations of the cosmic microwave background, interpreted through lambda CDM, predict a particular value for the Hubble constant. Direct measurements using distance ladders calibrated by nearby supernovae and Cepheid variables yield a different value, higher by about 9%. This difference, while seemingly small, is statistically significant and has persisted as measurements improve. Some researchers have proposed that solving the Hubble tension might require modifying cosmology, perhaps through early dark energy or other extensions to lambda CDM. Others argue the discrepancy might arise from systematic errors in either measurement. The debate continues, and it's possible that both measurements are correct, revealing genuine new physics. Webb's early galaxy problem might be related to the Hubble tension, or it might be entirely independent. Time and better data will tell. What makes the current situation both frustrating and exciting is its ambiguity. We're not witnessing a clear crisis that obviously demands revolutionary new physics, nor are we seeing straightforward confirmation of existing theory. Instead, we're in a period of tension where observations push at the boundaries of what models predict, where conventional explanations strain but don't quite break, and where exotic proposals proliferate but none yet proves compelling enough to gain consensus acceptance. This ambiguity reflects the nature of scientific progress. Revolutionary discoveries don't always announce themselves with trumpets and unmistakable signs. More often, they emerge gradually from accumulating anomalies that resist conventional explanation until someone finds the right new framework to make sense of them. The history of cosmology includes several such periods. The recognition that the universe is expanding, the discovery of cosmic acceleration, the realization that most matter is dark. Each began with puzzling observations that didn't quite fit existing models. Whether Webb's early universe discoveries represent another such watershed moment or will ultimately be explained within the current paradigm remains unclear. What is clear is that they've reinvigorated cosmology as a dynamic, contentious field where fundamental questions about the universe's nature remain open for investigation. The practical implications extend beyond abstract, theoretical debates. If the early universe did operate differently than we thought, with more efficient structure formation or alternative black hole seeding mechanisms, this affects how we interpret all observations of distant cosmic epochs. It influences our understanding of Ryanization, the process by which the first stars and galaxies cleared the fog of neutral hydrogen that filled the early universe. It impacts predictions for future observations, including what the next generation of even more powerful telescopes might discover. It also affects our understanding of life's cosmic context. If massive galaxies formed earlier and more abundantly than thought, this potentially pushes back the epoch when planets could form, when chemical enrichment reached levels supporting complex chemistry, and when the conditions necessary for life might have existed. The cosmic timeline for life's emergence could be longer than we realized, with profound implications for questions about life's prevalence in the universe. Ultimately, Webb's discoveries remind us that the universe retains its capacity to surprise. For all our sophisticated models and powerful instruments, we're still students of a cosmos that repeatedly demonstrates it's stranger and more wonderful than we imagine. The ongoing investigation. As the initial shock of Webb's discoveries subsided, the astronomical community settled into the systematic work of confirming, refining, and understanding these early universe puzzles. The first phase of observation, broad photometric surveys that identified candidates, gave way to a second phase of detailed spectroscopic follow-up that would determine which apparently massive galaxies were genuine and which were imposters. Spectroscopy, the technique of splitting light into its component wavelengths, provides far more information than photometry, which measures only total brightness in broad wavelength bands. A spectrum reveals the detailed pattern of emission and absorption lines created by specific elements and ions in the galaxy. These lines serve as fingerprints, identifying chemical composition, determining precise distances through the Doppler shift, and revealing physical conditions like temperature, density, and ionization state. For the most distant galaxies, Webb's near-infrared spectrograph, NIR-SPEC, became the essential tool. NIR-SPEC operates in two modes. The integral field unit mode observes a small patch of sky at high spectral resolution, ideal for studying individual bright galaxies in detail. The multi-object spectroscopy mode uses configurable microshutters to observe dozens of objects simultaneously, perfect for confirming large numbers of galaxy candidates. Through 2023 and 2024, multiple large spectroscopic surveys targeted the high redshift galaxy candidates identified in Webb's early imaging campaigns. The JDS program, JWST Advanced Deep Extragalactic Survey, led by teams from the United States and Europe, obtained spectra of thousands of distant galaxies. The GLASS program, Grism Lens Amplified Survey from Space, used gravitational lensing by massive galaxy clusters to magnify and brighten distant background galaxies, making even faint objects accessible to spectroscopy. These spectroscopic campaigns revealed a complex picture. Some candidates confirmed as genuine high redshift galaxies, their spectra showing clear emission lines at wavelengths consistent with photometric estimates. Others turned out to be closer than expected, their red colors explained by dust rather than extreme distance. These interlopers illustrated the challenge of photometric selection, where galaxies at different distances can appear similar in broadband colors. The confirmation rate varied depending on selection criteria and target brightness, but overall, a substantial majority of the brightest, most massive candidates proved genuine. This validated the photometric selection techniques while also showing they weren't perfect. More importantly, it confirmed that Webb was indeed seeing a population of massive galaxies in the cosmic dawn that exceeded standard model predictions, even if not quite as extremely as the most pessimistic early estimates suggested. As spectra accumulated, researchers could also begin studying the physical properties of these early galaxies in detail. The emission line patterns revealed information about ionization state, often indicating hard radiation from either intense star formation or active galactic nuclei. Some galaxies showed broad emission lines, characteristic signatures of rapid gas motions around supermassive black holes. Others displayed narrower lines typical of ionized gas in star-forming regions. Metallicity measurements provided insights into chemical evolution. Even the earliest galaxies showed signs of elements heavier than helium, confirming that at least one generation of stars had already formed and died, creating and dispersing heavy elements. The measured metallicities were generally low, typically 10 to 30% of solar values, consistent with young galaxies still in early stages of chemical enrichment. But the mere presence of metals confirmed these weren't pristine population 3 systems. Star formation rate. Indicators derived from emission line strengths confirmed that many early galaxies were forming stars vigorously, often at hundreds of solar masses per year. Some showed evidence for recent starburst activity, intense episodes of star formation that might have temporarily boosted their brightness and apparent mass. Others appeared to be forming stars more steadily, though still at rates high compared to typical modern galaxies. The AGN fraction emerged as a key question. How many early galaxies host actively accreting supermassive black holes, and how much does AGN emission contribute to their observed brightness? Early estimates suggested AGN might be present in 20 to 40% of massive, high redshift galaxies, though this varied significantly depending on selection criteria and how AGNs were identified. Developing reliable AGN diagnostics for high redshift galaxies proved challenging. Traditional techniques like the BPT diagram that plots certain emission line ratios to distinguish AGN from star-forming galaxies were designed for low redshift galaxies with near-solar metallicities. At high redshift, with lower metallicities and higher ionization parameters, star-forming galaxies can occupy regions of diagnostic diagrams normally associated with AGN, leading to confusion. New diagnostic approaches were developed specifically for high redshift galaxies, using different combinations of emission lines and accounting for the different conditions in the early universe. These refined diagnostics generally reduced the estimated AGN fraction somewhat, but still indicated active black holes were common among the most massive early galaxies. X-ray observations provided independent evidence for AGN. Active black holes emit copious X-rays from their hot accretion disks, and X-ray detection offers a clean AGN signature largely immune to dust obscuration. NASA's Chandra X-ray Observatory conducted deep observations of fields previously surveyed by Webb, detecting X-ray emission from some high redshift galaxies and confirming they host active black holes. However, Chandra struggled to detect many candidates, either because they were too distant and faint in X-rays, or because dust absorption blocked even X-ray emission. Future X-ray missions with greater sensitivity will be needed to fully census the AGN population at cosmic dawn. Through 2024 and early 2025, patterns began emerging from the accumulating data. The most massive early galaxies did tend to show AGN signatures more often than less massive systems, consistent with the idea that rapid black hole growth contributed to their brightness. Dusty red galaxies were particularly likely to host obscured AGN, with the dust absorbing much of the AGN's ultraviolet and optical light, but allowing infrared and X-ray emission through. Yet, even accounting for AGN contributions, a significant population of genuinely massive, star-forming galaxies remained in the early universe. These galaxies weren't AGN-dominated. Their spectra showed characteristics of stellar populations with masses reaching tens to hundreds of billions of solar masses. The number of such galaxies still exceeded lambda CDM predictions by roughly a factor of 2, an excess that couldn't be easily dismissed as measurement error or selection bias. This factor of 2 excess might seem modest compared to the extreme initial claims of impossibly massive galaxies, but from a theoretical perspective, it remained significant. Lambda CDM makes specific statistical predictions about galaxy abundances. Finding twice as many massive galaxies as predicted suggests either the model's parameters need adjustment or some physical process not properly included in simulations was important in the early universe. Systematic uncertainties complicated the picture. Mass estimates depend on assumptions about stellar initial mass functions, dust content, stellar population ages, and other factors. Different research groups using different analysis techniques sometimes obtained significantly different masses for the same galaxies. Resolving these discrepancies required careful intercomparisons and development of standardized analysis pipelines. Simulations also evolved in response to Webb's observations. Groups incorporated more sophisticated treatments of star formation, feedback processes, dust production, and black hole growth into their models. Some found that including previously neglected physics, like radiation pressure feedback or more realistic dust models, could boost early galaxy masses and abundances toward observed levels without changing cosmological parameters. One important insight emerged from simulations of bursty star formation. Galaxies don't form stars at constant rates. They undergo periods of intense activity interspersed with quieter phases. If you observe a galaxy during a starburst, it appears brighter and more massive than its average state. Survey observations that sample galaxies at random times will preferentially detect them during bright bursts, creating a bias toward apparently massive systems. When this time variability effect was properly accounted for in simulations and observational analysis, it explained part of the excess of bright early galaxies. Not all, but a significant fraction. combined with revised star formation efficiencies, more realistic dust models, and accounting for AGN contributions, the gap between theory and observation narrowed substantially from initial alarmist estimates. By early 2025, the narrative had shifted from crisis in cosmology to interesting tension requiring further study. The situation resembled many previous episodes in astronomy where initial dramatic claims moderated as data quality improved and analysis techniques refined. This pattern doesn't mean the initial excitement was misplaced. Often, the process of investigating apparent anomalies, even when they ultimately resolve in favor of existing theory, reveals important details about how physical processes operate. Looking forward, several key observations would help resolve remaining uncertainties. Deeper spectroscopic surveys of larger samples of early galaxies would improve statistics and reduce the impact of individual outliers or selection biases. Higher signal-to-noise spectra would enable more detailed studies of stellar populations, allowing better discrimination between recently formed stars and older populations. ALMA, the Atacama Large Millimeter/Submillimeter Array, a ground-based telescope array in Chile, would provide complementary data on dust and gas in early galaxies. ALMA observes at millimeter wavelengths, allowing it to detect cold dust and molecular gas that Webb can't observe directly. These observations would constrain dust masses, molecular gas reservoirs available for star formation, and dynamical masses derived from gas kinematics. Future missions would push even further. NASA's Nancy Grace Roman Space Telescope, scheduled for launch in 2027, will conduct wide-field surveys covering much larger areas than Webb can observe, providing statistics on rare objects. Ground-based, extremely large telescopes currently under construction, like the Giant Magellan Telescope and Extremely Large Telescope, will offer higher spatial resolution and collect more light than Webb, enabling studies of internal structure and kinematics in distant galaxies. And, perhaps most importantly, continued Webb observations themselves would accumulate. The telescope's mission lifetime extends for at least 10 years, possibly longer. Each year brings new observations, deeper integrations, larger samples, and refined analysis techniques. What seems anomalous now might be routine in 5 years, either because we understand it better or because we've discovered it's actually normal, and our initial theoretical expectations were simply wrong. Science progresses through this iterative process of observation, hypothesis, testing, and refinement. Webb's early universe discoveries represent one chapter in an ongoing story, a story that began with the first telescopes turned skyward and will continue as long as humanity looks up and wonders what lies beyond. Conclusion. As you drift towards sleep or simply rest in this moment of calm contemplation, let yourself marvel at what we've discovered together. The James Webb Space Telescope has opened our eyes to a universe stranger and more wonderful than we imagined. A cosmos that doesn't easily yield its secrets to our theories and models, but instead challenges us to think deeper, look more carefully, and question our assumptions. Those impossible galaxies, shining in the cosmic dawn when the universe was barely out of its infancy, remind us that existence itself is more remarkable than any story we could invent. Whether they ultimately confirm our current understanding of cosmology or demand revisions to fundamental theory, they speak to the richness and complexity of the universe we inhabit. Science is not a collection of fixed facts, but an ongoing conversation between human curiosity and nature's mysteries. The astronomers studying these distant galaxies, the theorists wrestling with their implications, the engineers who built Webb itself, they're all engaged in humanity's ancient quest to understand our place in the cosmos. And now, through their work, we can see further back in time than ever before, witnessing the universe when it was young, when the first structures were forming, when the story whose latest chapter we inhabit was just beginning. Rest now in the knowledge that the universe continues its patient revelation. Tomorrow brings new observations, new insights, new mysteries. The cosmic dawn holds secrets we're only beginning to uncover, and the journey to understand them has only just begun. If you've enjoyed this exploration of the impossible galaxies at the edge of time, please like this video and subscribe to the Science Pillow for more calming journeys through the wonders of science and the cosmos. Until next time, sleep well and dream of the stars.